for a certain type of computer chip, the probability mass function of the number of defects, x, is represented in the following table, right? So they have, let's say, 100 chips, and x is the number of defects, right? So the probability that 0 from a certain sample are not defected is 40%, 1 is 30, and so on, right? So now we want to figure out some details about the probability mass function. Can you guys see this, or should I zoom in a little? Because I know the brightness is a little high. Right? Can you just see it, or zoom in? Let me make sure I know how to zoom in. You know?
Oh, it's different.
Or do yeah, is it from here?
No, it's going to be. Is it like an?
Yeah. Oh, yeah, right here. Yeah, that's fine. That works.
Is that good?
Yeah, that works, right? Yeah. It's online, and if you Google SARC, you see Google Sites SARC, and then on the left-hand side it'll say statistics and my name, and it's right there. It says practice final towards the bottom. Yeah, and it's also in the announcements. Irene made an announcement earlier, or yesterday, and she posted it too. She posted the link anyways. So yeah, so here's the problem. Here's the probability mass function. So the part A is asking the probability that x is less than or equal to 2, right? So this one's pretty simple. If you can just get the gist of probability mass functions, you know that you're already given all of the probabilities here, so they want to know from here down, right? So you're just going to add up probability of it being 0 plus the probability of it being 1 defect and the probability of 2 defects, because it's including. Because in this case, it matters when it says including 2, right? Because it's a discrete probability mass function, right? So from this, we'll have 0.15 plus 0.3 plus 0.4 ends up being 0.85, right? Simple enough, right? If you guys can refresh your memories. And now, for B, they want probability of x being greater than 1, right? So obviously, for this case, we're not going to include 1. Or we can just do the easier case, would be, instead of adding all these numbers up, we can just do 1 minus the probability of x less than or equal to 1. Right, which is 1 minus 0.4 plus 0.3, which, as you might be able to see, is 0.30. And if you do it the other way around, you should get the same answer. Simple, right? And now we have, I know Salim stresses or emphasizes that most of your analysis is done on the mean, population mean, sample mean. It's usually about finding out the mean, right? So this is from way back when, and the simpler case of it, so that you can get used to being able to calculate the population mean, right? So here, for the mean, if you remember, each data point multiplied by the sum of each data point multiplied by its respective probability, right? Probability of it occurring, which would be the sum of each one, right? So if I do 1 times 0.3 plus 2 times 0.15 plus 3 times 0.1 plus 4 times 0.05, right? And that should all equal up to 1.1, right? And what does that tell you about the distribution that we have, right? If the mean is, let me bring this down. If the mean is somewhere here, right? You guys tell me if it's skewed to the left or skewed to the right. Skewed to the right, right? Because there's more values on that side, right? Yeah, so that's something that she would ask you, one of the multiple choice questions, something that, but it's easy to kind of mix up, because I know a lot of people mixed up the skewness of a distribution. But all right, now we can go to the next problem. So a chemical supply company ships a certain solvent in 10-gallon drums. Let X represent the number of drums ordered by a randomly chosen customer. Assume X has the following probability mass function, right? So let me bring this up. So the first one says find the mean, right? We already know how to find the mean, because this is something that she asks all the time. So we do, for number 2, we'll do A. Right, so once again, the mean should just be the summation of X times P of X. And the usefulness of this is that sometimes you're going to need the mean anyways for a second part of the problem or third part of the problem. Like you've seen her always have steps throughout her problems that have to do with the prior, and if you get one wrong, then you're probably going to get the rest wrong, right? Or that's a way to make sure that you got it right. So this is going to be 1 times 0.4 plus 2 times 0.2 plus 3 times 0.2 plus 0.2 plus 4 times 0.1 plus 5 times 0.1, right? Which should be about 2.3, right? 2.3, so not exactly in the middle, right? Once again. So then they want the variance. Variance shows the variability within your data set, right? So we all know that the equation is going to be, well, there's the shortcut and then there's the long way of doing it, where you'll sum up each x minus each x minus the mean, right, times the probability of them, if you guys can remember, or squared. That was for the variance. Sorry. Right? Not standard deviation, variance. Right? So then, we can do this the long way, but I'd rather do the short way, which is also summation of, what is it? X squared P of X. Right? X squared P of X. Let's do E of X. E of X squared times or minus E of X quantity squared, right? If you remember. So then we can just go and do 1. For each one of these, we're just going to square the given x and not the probability, right? So it's 3 squared, 0.2 plus 4 squared times 0.1 plus 5 squared times 0.1, which ends up being about 1.81. And you can do this on your own if you like doing the long way, just to see if you're doing it right. And if you do them both ways, then you can obviously tell yourself if you actually got the right answer or might have messed something up. Yeah, if you have a question.
Is there any instance where using the long way is going to be more efficient than the shortcut?
No, that's why it's called the shortcut form. Because some people I know actually prefer doing the long way because they just like seeing it all out like that and then calculating it in their calculator. But I don't really see the point of actually, because like I said, with this one in A, I already gave you the mean, right? You already calculated the mean, so we could just do 1 minus the squared, right? And then that's going to be about, 2.3 squared, right? And that's going to be about 1.81. Sorry about that. But like I said, you could just use what you've already found instead of doing it the hard way, and save time, because there's a lot of problems that she puts on her exam, right? But like I said, it's preference. If it works for you, then that's the way you can do it. Now we want to do standard deviation, which ends up being just the square root of the variance, right? It's just the square root. Or let me just do of 1.81, right? Which is about 1.345. So can you guys tell me if there's large variability or small variability? Or how can you tell? Large? You could just say large or small. No. Large? Yeah, it's large only because the numbers you're dealing with, it's 1, 2, 3, 4, and 5. So if you have a difference of about average difference of about 1.3 within such a small interval, then you know that your data points are scattered all around, right? So it's a good way to interpret your data instead of just like looking at the formulas and just, okay, that's all I have, because that's just how you can tell what you're working with, right? So then D changes the problem around and tells you that they want to analyze what Y is, and Y is the number of gallons, and they already told you that these are 10-gallon drums, right? So now they want the probability mass function of Y given 10-gallon drums, right? So for this case, if you do for Y, P of Y, what do you think should change, or what is supposed to change? How do we interpret it? Yeah, because it's 10-gallon drums, and we already know that these are just the given drums that we have, the number of drums. So if we do 10 gallons, then it's 10 per each one, right? 20, 30, 40, 50, right? And still the same probability for each one, because now we're just dealing with the weight of the same values, right? So simple, but it's easy to misinterpret questions like these. So now if you have the mean of these, it shouldn't just be what was the answer for this one? 0.85. Yeah, so it's not going to be just 10 times that, right? So if we go for Y now, we'll do 10 times 0.4, right? Simple, same procedure. And these problems will get tougher, promise. It's just that the earlier chapters kind of set you up for the info that you're going to have later on, right? And this ends up being about 23 gallons, right? So your average weight is 23 gallons for the data that you're dealing with. And now if you do the same variance and standard deviation, since standard deviation, we can go do the shortcut method again. E of x squared minus E of x, or E of y, sorry. E of y squared, so that we can know for each one, 0.4 plus, hold on. Squared times 0.2 plus 30 squared, right? So when you get asked a question like this, then you already know what to expect out of your data and how to interpret your answer that you have, and if it's going to be way off or if it's actually in line with the data that you're given. 0.1 minus the 23 squared, right? And that should be about 181. So this one ends up being just the square of the difference that we got from the other one, right? Instead of multiplying times 10, it ends up being multiplied times 100. So then the y that we have is just 181, 13, 4, 5, right? All right, so now number 3, and that's simple enough if anybody has any questions before we move on to the next question. So the lifetime of a battery in a certain application is normally distributed with a mean of 16 hours and standard deviation of 2 hours. What's the probability that a battery will last more than 19 hours, right? So now the whole gist of these type of problems is that it's not like the ones before where you're given the distribution. Now you're kind of guessing, right? Now you're guessing, and the way to guess for these given cases is using the z-value, right? As long as it's a normally distributed function, or it can be the chi-squared, beta functions. It all depends on what they tell you that the distribution is, right? The probability distribution. In this case, it's normally distributed, which is the simplest case and the most convenient case because we have the tables that she'll provide you to interpret what the behavior of your data is. Right, so for 3, we have, what is the probability that a battery will last more than 19 hours, right? 19. We know that for this case, the mean was 16 for the whole population, and the standard deviation was 2, right? So since it's normally distributed, the first thing you want to do is standardize it, right? Because the z-table is all standard normal. So we have a normal distribution, now we want to make it standard. So for 19 hours, that it's x minus mu over that, right? So we want to inspect 19 hours. What's the probability that it'll last longer than that? this ends up being 1.5. So then the probability of x being greater than 19 is the same as probability of z being greater than 1.5, right? So we know that the z charts give you the area to the left. We want area to the right. So it's going to be 1 minus whatever you find out for that z value, which is, oh, I didn't write it down, but, well, I don't have the z charts with me, but I calculated it beforehand. But it should end up, if anything, that's better for you guys to go back and see if you get the same answer, right? Oh, yeah. So we'll do 1 minus, so now you don't have to look at it yourself. Z value is going to be 0.9332, right? Thank you. 0.9332, which would hopefully come out to be about 0.0668. All right, the probability that, so it's small probability that it's going to last longer than 19 hours if we know that the average overall is about 16. So now for B, they want the 10th percentile for A, B. So now they want the 10th percentile, so then that's just a different way of asking the question. But it does stump some people when you ask the same question in a different way, even though they're not going to ask you something that you don't have the tools to understand or evaluate yourself, right? So for this case, 10th percentile is going to be what? What does the what does a percentile indicate? Probability of being greater than would be 0.1.
Probability that C is greater. We're looking for the value of C that we know the probability of 0.1.
Well, yeah, the probability of your z value, yeah, being with a probability less than, well, so this area, probability of the z value, like he said, should be 0.1, right? It's only greater than 10% of the data set that you have, right?
What about the possibility of it being the upper?
Well, upper 10? Then there would be, yeah, right? It would be, if it's,
there's like 3 ways of looking at it.
yeah, so, but the whole thing about percentiles is of that given z value being greater than, right? That's what the percent, so if I say 10% is going to be somewhere here, right? If I say 50%, then it's obviously the mean, right? But if you'd want...
So you specifically, when you say the 10th percentile, you specifically mean
the
that
area below
the
it.
probability of z being less than this value
Right.
is equal to 0.1.
Correct. Yeah, if that makes sense. So then all you want to do is look for that z that corresponds to that percent. And sometimes you won't have the exact number, right? Sometimes they jump to a different number. So here's where you round. It's not that big of a difference. So for this case, well, let's look. So 10% is about, I got negative 1.28, so we'll see. Negative 2.8, yeah. So see, somebody could pick 1.27 or 1.28. I chose 1.28, but either or, it's about the same. So I got my z value to be about 1.28, right? Which means that the x minus the mu over is equal to 1.28, right? So all you have to do is solve for that x in this case. So simple you already know the mean, you know the standard deviation. So some algebra will get you 13.44, right? So if you have an average value of a lifetime of 16 hours, then
That 1.23 or 1.28.
which one? Oh, 1.28 right here. Negative 1.28. So about 10% of your data or of your light bulbs or whatever thing that you're observing. Here it's the battery, actually. So 10% of the batteries that you have a life cycle of about 13 hours, right? And that's good to know when you're trying to organize anything that you're given. So, right, so that makes sense with percentiles. So now we go to number 4 that says resistors labeled 100 ohms. Resistors are labeled 100 ohms. In fact, the actual resistances are uniformly distributed on the interval 95 to 103. Find the mean, standard deviation, and then the probability of a certain interval, right? So for 4, we have, let's see. We have, to find the mean, you can do x, which is about 95, 103, x times your uniformly distributed function, right? And what's another way of just finding if you have it uniformly distributed other than integrating it? If you guys know. If it's uniformly distributed, right? So that means that it's like this. So it's 95 to 103. This is P of X, right? Yeah. Right? It should be the median since it's uniformly distributed, so it's somewhere in the middle, right? And the hard way of doing it would be to integrate it if you didn't have that knowledge that, oh, hey, it's uniformly distributed. I can just divide the two, right? Add them and divide them. Well, the next step would just be dividing it, right? It would be, what is this? 103, so 8. So 2 times the 8, right? And evaluated at 103, which magically ends up being 99, which should be the 103 plus the 95 divided anyways. Somewhere in this interval of right? We have that's number 4. Exam, so.
Well, not. This one's simply not.
What is it?
No, let's keep.
Right, so So now this will be the last one of those, 4, right? Which ends up being 0.6. So most of your data set falls within that range, right? For C, we have the marginal probability mass function. Find the marginal probability mass function P of x, right? So Px of x is going to be something. So what would be the probability for, or the probability mass function for x, when x is 0? .26, right? When x is 0. What about when x is 1? 0.48 when x equals 1, and for x equals 2, 0.26, right? And to check his math, we can see, so this is 12, 0, 1, 4, 6, 8, 4, 6, 8, 9. Wait, actually, is that right? Oh. I might have wrote one of the numbers down wrong. But it should be equal to 1. Maybe it is equal to 1? Oh, I'm just adding wrong then, right? Oh, yeah. Okay. It should be 2 up here. Yeah. Well, there you go. Even the algebra ends up getting some people, like I said. So for the same, we do the same procedure, just add up. This time for y, we add up the columns, right? So we add up the columns, which end up being 0.33, 0.48, and 0.19. And you can check my math because I clearly am able to mess up. Right? Now we want the mean of y. And the mean of y can be found in 2 different ways. Well, I'll do mean of x too, I guess. So I like to use the probability mass function, like I've said before. So instead of having to add all these up, you can just do this times this plus this times this, right? So it'd be 0 times 0.33 plus 1 times 0.48 plus 2 times 0.19. It ends up being 1. So it's right in the middle. And then for x, or sorry, it shouldn't be right in the middle. That's why I was like, wait. This one should be right in the middle because as you can see, it's evenly distributed, right, on each side. So it should fall into 1 for the x. So for this one, it would be 0 times 0.26 plus 1 times 0.48 plus 2 times 0.26, which should be 1. Simple enough, makes sense, and you can catch your mistakes like that. Right? So then for a conditional probability, yeah, I'll let you guys catch up. So for conditional probability, this one is the one that always, or that's the most confusing for some people, just because there's a lot more conditions. So for conditional probability, for this case, or is everybody done copying it down, just in case? Yeah. I know I might be going a little fast. When we get to the harder problems, I'll like slow down. Oh, the answers? Yeah. I'll post the answers online, yeah. And it's streamed, so you can just watch it online too, on top of that. If you, probability mass function of P of y, right? P of y given x when y, for y is 0, right? So they want the entire probability mass function of y given that x is 0, right? So how do we find that? We have to actually do each case, right? So when y is 0, when y is 1, when y is 2. So I'll do when y is 1, or when y is 0 first. So given that y is 0, would be the probability that y, or xy. So the probability that divided by the condition, which is the probability that x is 0, or you could just use the probability mass function instead of just adding up the rows again. So the probability that you have 0, 0 is 0.1 here, right? And we already computed the probability of x being 0 from the probability, or the marginal probability mass function, which is 0.26, right? So this was 0.1. You can get the answer like that. So probability of y being x for y is 0. So probability of 1, 0 over the same condition, right? They all have the same condition. 2, 0. Probability of 2, 0. X being 0. For what is this, y? 1, 0 is 0.11. 0.11 divided by 0.26, and then 2 is 0.05 divided by 0.26. So then the probability mass function, or the marginal probability, is y 0 about, so this is what I got. Y 0 0.4231 when y is 1, and 0.1923 when y is 2. That's probably the hardest type of question you can get from a mass function, or a probability mass function, when we're talking about discrete. And probably the same, yeah, conditionals are probably the toughest questions out of those that you can get from chapters 3 and 4, but nothing too crazy, right? So now we can jump to chapter 5. Chapter 5, you kind of just have to understand the distributions that you have and different characteristics, different cases. So here it says a catalyst, number 6. A catalyst researcher states that the diameters in microns of the pores in a new product she has made have the exponential distribution with parameter lambda is 0.25, right? So lambda being 0.25. For exponential distribution, we have a whole bunch of equations that we can memorize, but the most important parameter for exponential is the lambda that they gave you. And they could give you the lambda in a bunch of different ways. Like for this case, where the mean for exponential distribution is going to actually be the inverse of your lambda value. And the same for, I believe is the same for standard deviation. We said 1 over 0.25 should be 4. And then the same for this, 1 over 0.25 ends up being 4. Right? So they could give you the mean without giving you lambda and then try to expect you to figure it out. Yeah. I believe it is. What is it? Oh no, that was 1 over 4. 'Cause I was just,
Is that 4 from the mu, or is that 4 from the
well, the 1 over 4 is just the 0.25.
So sigma and mu are confused, but
Sigma and mu are the same, yeah. They're going to be the same in this case.
is that every case in exponential?
Oh yeah, probably. Right? Yeah, it should probably be the same for each case. And you can check on if I'm wrong on that for the equation, but I'm pretty sure that's what it was for exponential. For exponential, anyways, that's a specific case.
Right, so the sigma, the standard deviation is always equal to the mean on this?
That's what the equation ends up being. Right? So then, for C, what proportion of the pores are less than, so proportion of the pores are less than 3 microns in diameter, right? So X being less than 3, right? So for this case, they give you the formula for the distribution, so you don't have to integrate it out every time, which should be 1 minus e to the negative x. And that's why lambda is important, or else you won't be able to find the probability at any time, right? And this is for the left-hand side of the exponential too. So 1 minus e to the negative 0.25 times 3 ends up being 0.5276. And D is which one is greater than 11. Probability that x is greater than 11. right? For this case, we do -0.25 times 11. You plug it into your calculator and get 0.0639. And then we have the quartile question again, or you said percentile last time. But what is the third quartile of the pore diameters? So if you remember when we were talking about percentiles, what would the third quartile be in this case? 75th? 75th, yeah. So now you have the 75th percentile. So third quartile is the same as the 75th percentile. Right? When you break it up into 4 pieces, you'll have 75th. So we have the same equation. 125x is 0.75, right? So the probability that it's that 75% of it is below that given value. And you'll have e to the negative 0.25x equals 0.25. And then your x ends up being 5.55 microns. So out of the pores that they've collected, the ones with diameter 5 are 75, or is greater than 75% of the whole data that they have. Right? You know, I'm kind of going faster than I hoped to, and we kind of have like 2 hours here. So let me slow down for these. So at a large university, I'll ask questions. So at a large university, the mean age of the students is 22 years. And the standard deviation is 4. A random sample of 64 students is drawn. What is the probability that the average age of these students is greater than 23? So the last question? For D? No. Right. Part C. What value? Is the 3 here. Just plug in the 3. Just how for D I did the same, just plugged in. Because it's either the left-hand side or the right-hand side. This would, you subtract it from 1 because, you know, to get the left-hand or the right-hand side. Yeah. Right? Yeah. That's how I got those values. Right, so, but for this question, we have, at a large university, the mean age is 22. What's the probability that the average age of these students is greater than 23? So how do you approach this problem when you don't know a lot, right? What do we know, though? Standard deviation, the mean. So we know the mean, population mean, right, of 22. We know the standard deviation of 4. And we know the sample size, 64. Now they want what is the probability that the average age is greater than 23. Right? So how do you interpret that? You assume normal, right? Assume normal. Yeah. Because of the central limit theorem, for this case, they just said large, so you can assume it's really, really big compared to the 64 that you drew anyways. So now, if you assume normal, then we can go back to the same analysis that we did beforehand and use the z-tables to approximate what the value should be, right? So, what's the probability? We want probability that x is greater than 23, right? So we want to figure out what z is. So your 23 minus your 22 divided by, well, for this case, since it's really large, I do square root.
Average age, there's something that the average age is
Yeah. Or x bar if you want. Yeah. The random variable that you're dealing with is the mean already. So you're trying to approximate what the value of the mean is. So we have square root of, is it, that would, right, no actually, what is it? The square root, right? Yeah, that's what I was gonna. 23 yeah, so after you plug in these values, I got 1.4, right? So I had written square root over the whole thing. That's why I was like, I don't think that's right. Which you can find back on the z-table. 1.4. And this is 1 minus 0.9192, which is about 8%. So there's an 8% chance that your average value, average age, is greater than 23. Because if you find this on the z chart, like if you just go to the z chart and plug in the z value, for ours is 1.4. So 1.4 here. It's going to give us this area, which is less than the value that we want. But for our case, they were asking greater than 23, right? So this is the value that we used, but there's not a 90% chance that it's greater. But that's a way to misinterpret what the z-table is telling you, right? So now we have chapter 7 and 8. So now we're going to get into the null hypothesis stuff, which is kind of like the bulk of the exam. And a lot of it is going to be what I went over. But null hypothesis stuff, I felt like I got those stuff mixed up. That was probably the stuff that I got mixed up the most when I was taking the class, because there's just different ways of rejecting or not understanding what the p-value is. But that's why we're going to go over it now. Yeah, number 8 I just did for like an exercise because we end up using these in the problems. So, is it this one? Yeah, so, all right, so we're going to start with 9. I'm going to skip 8. So we're going to jump to 9. So the capacities were measured for a sample of batteries, 120 batteries. The average was 178, and the standard deviation was 14. Find the 95% confidence interval. 95% confidence interval for the mean capacity of batteries produced by this method. N equals 120. So you ran an experiment. Like, let's say your boss gave you 120 batteries and told you to figure out the capacities so that they can write it on their requirements for the packaging. You run the experiment and you figure out that the average is about 178, the standard deviation of 14, right? Just for your given sample. And now you want to figure out a 95% confidence interval for all the batteries that you have at that factory. And your boss is going to tell you what kind of confidence interval they want, you know, what's acceptable. Anything below that, they don't want. They want to be certain about what they write on the packaging. So usually the most common one is 95% confidence interval. So for this case, yeah, this is usually the most common one. Sometimes they'll give you 99, but we'll go over all of them. So from the number 8, you'll figure out that what the Z value was for that. I can just write them actually, just so I have them. So I had 1.96, 2.33, 2.58, and 1.28. Right? So for this case, we have a 95% confidence interval. So we want to say that 95% of our data falls in here, and only 5% of it falls somewhere here, right? So based on the sample that you ran an experiment on, you can figure out the endpoints. So your true value for the entire collection of batteries that you have can be found with some given confidence level. And that always depends on how accurate, what's more important, accuracy or being precise? Is it how narrow, how wide of a confidence interval you actually want, right? So for this case, we're going to have 178 plus or minus, what was it, 1.96 square root of 120, right? So with this, you're going to have the two endpoints of your confidence interval, and the Z value here is what allows you to have 95% within this range. And that's how you can tweak the confidence interval level, right? But at this Z value, we know that there's only 5% that's going to be on both sides together. So when you let them know what your speculation is going to be that or it should be that the true value of all our batteries, the true capacitance should be at about 175 to 180, and it's a wide range. Yeah, it's a wide range that can be shrunken, but then you'll be less certain if it actually falls in there. It can be, if you increase it, obviously, then there's less numbers for it to not include. So you can be more certain, but then it could be any number. It'll be like 160 to 190. And it's like, well, what help does that do to me, you know? So, yeah, so this is going to be the confidence interval for this case. And for B, they want 99%. So A was here. So now we want a 99%. Like I said, it should widen the confidence interval, right? Confidence. So for this one, we said 2.58. So now we still have the same values. So N is 120. The mean is 178. S is 114, right? Except now we have like about somewhere here. So yeah, you have you're going to be more confident about the values that you do end up getting. But that's only because you're letting in more values that might be wrong, right? But with this case, it's going to be 178 plus or minus 2.58, 14 to the square root of 120. So this one's going to be 1 or 1. Oh, for the, yeah, oh yeah, that is true, yeah, for 2. So for 95, right, for 95%, you want to, well, there's 2 ways of doing it. So you can look here and look for 95. No, actually, no. So the way that I do it is I just go to the look for the alpha. So for 95, alpha is going to be 5%, right? So I'm going to look somewhere here for 5%, and you end up, so probably this one right here, right? But then that's for Z alpha, right? Now you want alpha over 2 because you have an interval, right? So you want it on both sides. So yeah, alpha is 5, but you're going to have 5 combined, right? So now you want to look for, what is it, 2.5. So 2.5, this right here, 2.5, right? But this is the one on the left, right? So this is negative 198, 196, and this is, so 196, Yeah, 196 here. Right? So you want the z value that has 0.25 or 2.5 on the outside of it, right? So here I have 1.96, and what did I use? Yeah, I used 1.96. So this one corresponds to some z value here, and this shaded is only 2.5, right? So then on the other side is going to be the negative 1.96. So that's why you do plus or minus here. So you're going to do 178 plus the 1.96, which will give you this one, right? And then when you do 178 minus, it'll give you the z value here. So then that'll be the range. And you just want it within that interval. And it's the same for 99. So if we look for 99, it's going to be 1%. So then you want 0.5, right? And I end up getting, what, 2.58. And if we work backwards from what I did, so 2.58, and then we'll do negative 2.58. 2.58. See, it's not really right at 0.5, but it's 0.49. So I just ended up going with that one because the other one is 0.51. So it's up to you which one you end up choosing. It shouldn't be off by that much. But yeah, I usually go to the negative z value, try to find what I'm looking for. And depending on if it's two-sided or one-sided, like if it was one-sided, you just look for the 1%. If it's two-sided, you have to divide it by 2 and find it that way. Yeah, so that's how you find the z value. And you should get the same ones that I found up here. So where were we? For part B. Yeah, so as you can see from, if you compare the two, you'll see that this one is a little bit wider than this one, right? And which is why you can say, oh, I'm more confident that my true value is in this one, but it just goes with your confidence level, what you're able to get away with. So now, C says, an engineer claims that the mean capacity is between 176 and 180. With what level of confidence can this statement be made? Right, so now we're working backwards. He's giving you a confidence interval. He's saying that it's somewhere between 176 and 180. And you're trying to figure out how high of a confidence level he has so that you can probably try to match it or make it better. So let's do the lower one first. So 176 is 178, because that was your mu, minus z alpha over 2, 14 over 120, square root of 120. That's for the lower bound, right? So then your z alpha over 2, if you solve for it, should be about 1.56. And then you try to look for 1.56 on the z table. And like I said, I go to negative first. Negative 1.56, which is about 5 or 6%, right? And that's for alpha over 2. So if you multiply it times 2, it's going to be like 12%, right? So then 12% is on the outside of it, right? So this is going to be about 6%, and then on this side he has 6%. So So this is 176 and 180. So then his confidence level is going to be about 100 minus 12, which is like 88. So about 88% confidence interval that he had, which is not good at all, right? Or usually you want to go with 90 and up. The rule of thumb is usually 90 and up. So his confidence level isn't that high, so it won't. So you could possibly make a better interval than he could. But it's precise though. It's a precise, right? It's a precise confidence interval because there's not that much variation. It's got to be somewhere in there. So next question. Next question has to do with p-values. I know p-values are a little confusing, but it's like working with the alpha value. It's what's not included. So this says that an article predicting profit performance for selecting candidate international construction projects presents an analysis of the profit of international construction projects. In a sample of 126 projects, the average profit margin was 8.24 with a standard deviation of 16.33. So the average profit margin in a sample was 8.24. Standard deviation of 16.33. So then a test is made where the null hypothesis is that your mean average profit margin is greater than or equal to 10. And to make it simpler, we always like to go with just equal to, right? But you have to know whether, when you're trying to pick the alternative hypothesis, you want to know whether it's going to matter. But for this case, if you have a higher profit margin, then that's what you want, right? So you don't want to reject that. So for this case, it's going to be, so what you want to reject is less than. So now we want to find the p-value. So find p-value. This is number 10, right? Yeah. So now we can do, we can find the z-value corresponding to this data. So 8.24 minus the 10 that you got, or that they're claiming, divided by the 16.33 over the square root of n. N is 126, or the square root of 126. Yeah. That ends up being about negative 0.121. And that's the z-value that you're looking at. Since this is less than, you're going to want to be looking at the, for this one, you want less than, so you want to be looking at this alpha. So it's not really going to be 1 minus for this case, right? So it's going to be whatever, negative 1.21. It's about 0.115. So 0.115. Yeah, 0.1151. So then that's what your p-value is. And in this case, like I said, when you want to reject or not reject, the rule of thumb is about 90% is being a good null hypothesis. So if it's going to be, for this one, it'll be like 89 or something, 89 or 89 or 88. So you don't want to reject that null hypothesis, right? Even though they didn't give you a significance level to match it to, usually it's you can match it to 90. If it's not better than 90, then it's no good at all. So for this case, we'd want to not reject. When you have really small p-values, that's when you end up rejecting. So number 11 says, do bathroom scales tend to underestimate a person's true weight? A 150-pound test weight was placed on each of 50 bathroom scales. The readings on 29 of the scales were too light, and the readings on the other 21 were too heavy. Can you conclude that more than half of bathroom scales underestimate weight? So what would be the null hypothesis and the alternative hypothesis? So what is it? Mu is less than 0.5. The thing about this problem is they didn't give you an average, right? They didn't. So if you wouldn't be testing. You wouldn't be testing a true mean value, right? Because they didn't give you a mean value.
So to be clear, that last one, they failed to reject.
Yeah, failed.
So we
Yeah.
So we count the
If you want me to write it on here. Yeah. You wouldn't reject it because it wasn't a good enough estimate. So for this case, this one's a special case because it's not mu, right? But what would it be? What do we have? We have that the question is, do scales underestimate a person's true weight? So can you conclude that more than half of bathroom scales underestimate weight? All we know is the number of scales that did underestimate and the number of scales that didn't underestimate. So, and we know the total. So what you can do is compare the proportion of them, right? The proportion of your sample, because you don't have anything else to compare it to. So let's say you include that more than half. So you're going to say the P is 0.5, and your alternate hypothesis is going to be more than 5, right? 0.5. Yeah, because if it's less than or equal to, then it's a good thing.
So then for the null, we should put, instead of equals, we should put less than or equal to, or?
Yeah, but Dr. Salim likes to just leave it as equals to not complicate it. Because then people will think, oh, do I have to find two-sided or one-sided or something? But she likes to keep it at equal to and then just compare greater than or equal, depending on the alternate hypothesis. So that's why I'm doing that. All right, so we'll leave it at equal to, but you can see that for this case, it would technically be less than or equal to 0.5. Right? So we can standardize the proportion this time, since it's greater than, what is it, 30? So we're going to do a different equation this time. We had 0.58. How many were there? It was 29 that did. So we're going to say 29 over 50. 29 over 50 did underestimate, right? In the sample that we had. So that's 0.58, right? Yeah. 0.58. So we're going to do, it's a different, for standardizing of proportions, a different equation. Or I can just write it. It's the P hat minus P over, right, success P Q over N. So our, that did underestimate was 0.58 compared to the 50 that we want, 0.5. The probability of success and the probability of failure is just 50%. You can either underestimate or overestimate, right? So 0.5, 0.5 over 50. The total number was 50, yeah. I didn't check that. So the number was 50. We don't want to check the 21 because those were the ones that overestimated. And this gives you a z-value of 1.13. And this is greater than this time. So you want the 1 minus your phi of 1.13. Right? Ends up being, well, 1.13. Minus 0.8708. So then the p-value for your given sample is 0.1292, right? So do you reject or not reject? Fail to reject because it's not good enough or small enough p-value. Right? So, yeah, that one's proportions. So it's different than what you're used to with the finding the true values. But that's definitely something that she does ask. So now for number 12, it says a new process for synthesizing methanol from methane is under study to evaluate its technical feasibility. Design simulations indicate that the reactor must have a mean methane conversion greater than 35 for the process to be feasible. In an initial study, 6 runs were made. The average conversion was 39 and the standard deviation was 4. If it can be concluded that the mean is greater than 35%, further evaluation of the process will be conducted. So the null value, well, actually, what makes this case different than the other cases? Or if it is any different? Can anybody guess if you want to read it? Right, n is small. So when n is small and you don't know your population deviation, it ends up being t value. So you see, so you're getting each case so that you get some exposure to each case. So they say that mu is 35. You want to compare it to 35. 35%. And it can be less than or equal to like the last one, but we're just going to say equal to. And then alternate hypothesis is mu is greater than 35. And like we said, is going to be a t-test. degrees of freedom is what you need. 6 minus 1, because 6 runs were made to find the data that you ended up finding. So that's the degrees of freedom. T-value is going to be the 39% that they found minus 35 divided by the standard deviation, which was 4%, divided by square root of n. Right? And this gives you 2.449. And we're testing greater than again, so we want the upper tail, or the upper tail of the t distribution. So let's see. Oh yeah, sure. It should be, yeah. Oh, thanks. So for here, if you do 2.449, so 2.45 for the t values. So actually, I could just guess one or the other. With a standard or degrees of freedom of 5, we'll say 2.5, I guess. 2.5. Is that? I can't hear you.
You can just say it.
Yeah. Yeah, you can like try to interpolate, but you can also just round. So we'll just say it was 2.449, so it's not really 2.5, so we'll say 2.4, so 0.031. So that's what your p-value ends up being. 0.031, right? And in this case, they said well, there's not a p-value or an alpha to compare it to, but like we said, this is a very small p-value, 3%. So you have a 97% confidence level. So you'd want to reject anything that they used beforehand, just because this is pretty small p-value. And then the last question. For 12? Right. Yeah. Yeah. I found a t value instead of a z value. And yeah. And use the t chart instead of so A8 automatically tells you what's on the right hand side as opposed to like the z value. You're right. If it's less, yeah. If it's 30, it'll be, yeah.
Actually, I think she said it was 30 for
For normal distribution. And 40 for, yeah.
40 for essential.
But I doubt she'll ask something that's that, you know what I mean? Because for central limit theorem, it's 30. If it's 35, that's what I'm saying. Like, that's kind of like, yeah. For central limit theorem, to assume that a distribution is normal, you have to have a sample greater than 30, right? But for t distribution, you have to have, or for, yeah, t distribution, you have to have it less than 40. So that's the, for t distribution, anyway. To assume that it's normal, which t distribution is, to assume that it's normal is 30. But then to actually say that it's distributed as t, it has to be less than 40. So if it was like 35, you'd probably use the, oh wait. 35, yeah, that's a weird range, so. Well, for 35, I don't even think you could assume that it's normal. That's the thing. Or wait, no, wait. If it's less than 35, you can't assume that it's normal. Yeah, okay, we'll go with that. All right, so last question says, an engineer takes a large number of independent measurements of the length of a component and obtains X, we'll say mean, of 5.2 millimeters, a standard deviation of 0.1, uses this information to find the p-value for a mean of 5 and not equal to 5. So we shall see. All right, for these, we're just going to assume that they usually provide you with a alpha value, but for these, we're just going to assume anything better than 90, you can automatically reject. .2 of 0.1 H naught equal to 18 is about mu is 5. H A is mu isn't 5. Right? So two-tailed, like we said. So for this one, it says a large number, so we can't use t. So we'll say z is 5.2 minus 5 divided by 0.1. Oh yeah, you don't know the n, but what? Oh. Well, you don't know the n, but you can just standardize it like this. So 2. Right? So the z value of 2 gives you 0.977. So probability of, if it not being equal to. So p-value, the p-value is going to be 2 times 1 minus 0.9772, which is going to be 2 times 0.0228, and this is about 0.456. So this is, again, a good enough estimate, a good enough p-value, a small enough p-value to be reject the whatever you already have. You can just hand back the data and say that because they're and it can be kind of hard to do. Onto that, and then that's your z value. Well, I have mine too.
Well, yeah, well, maybe.